right, welcome back, Ling statisticians. I'm coming to you at the end of a very long and hot day at the end of June here in Calgary, Alberta, which is fine because I'm actually going to talk about the weather by the time we're done with this lecture, which is about linear transformations. So maybe you can see where this is headed. And if not, we'll just dive into it. So linear transformations, what's that about? So kind of want to start this off with just a question. We've talked a little bit about various ways to describe distributions, talked about measures of spread, range, central tendency, so on and so forth, distribution shapes, so on and so forth. What games can we safely and fairly play with the data in a distribution such that it still sort of preserves the integrity of the distribution, as it were? I want to answer this question in a couple of different ways today by talking about linear relationships between one variable and another, but we'll keep going with this topic as we move on to the next few lectures in the series here. That's kind of the question we'll frame this discussion with, and we'll start off answering it by looking at a very small set of example data, a very mini set of example data, which it just includes these three numbers, 1, 2, and 6, because it's going to be easy to do some math with this, or at least not too taxing, hopefully. Anyways, the mean of this distribution is 3. So normally I walk the class through this on the board at the beginning of the class. I'm not going to crunch all the numbers as we do this. I might crunch a few. But hopefully you can see like the average or the mean value of 1, 2, and 6 is going to be 3. So 1 plus 2 is 3. 3 plus 6 is 9. Divide that by 3, which is the n of the distribution. You get 9 divided by 3 is 3. And actually, this is the point where I would kind of jog your memory a bit and say, well, what's the standard deviation of this distribution? And this, I think, I will talk you through before I show you the answer, and then I might show you how to calculate it yourself using a spreadsheet. But standard deviation, remember we kind of want to see how far each individual point in the data set it deviates from the mean, as it were, on average for the standard deviation. So the way we do that is we take the difference of each data point from the mean. So 3 minus 1 is 2. Square that, you get 4. Maybe I can do it this way, the old-fashioned way. So I've got 4 to start off with the first data point. 3 minus 2 is 1, and then you square that, you get 1. So 4 plus 1 is 5. We're going to sum our squared differences there. And 6 minus 3 is 3. Square that, you get 9. 9 plus 5 is 14. So I'll pause here and say I'm kind of doing this a little bit backwards just to make it a little bit easier to think about. I think the way I wrote out the equation when I talked about this last time is you are actually supposed to take this number and subtract the mean from it. So the x sub I would be like 1 minus 3. That gives you negative 2. You square it, you get 4. It winds up giving you or putting you in the same spot as, say, subtracting 1 from 3, so on and so forth. So it doesn't really matter the direction as long as you square it in the end. And the squared sums of differences for all three of these guys is 14. Then we divide it by n minus 1, right? So n is 3. There's 3 items in this sequence or distribution. So n is 3. Subtract 1 from that, you get 2. 14 divided by 2 is 7. And then you take the square root of that. So the standard deviation is going to be the square root of 7. Okay, that's a lot of talk. Normally I do that on the board, and I'm sorry for talking you all the way through that. But that's just in case you had forgotten how that process works. And this is just some random number. It's not random with respect to the distribution itself, but it doesn't mean that much here in this particular case. So that's how you calculate the standard deviation here. And what I want to do, if it doesn't get too hot and sweaty here, is to figure out what happens to the mean and standard deviation if we add 1 to each value. So we're going to tweak the data a little bit and see if we can get away with it. So we're going to add 1 to each of these three numbers. And that'll give us a sequence or a distribution of 2, 3, and 7. And maybe you can just stop and think for a second, what is the mean value of these three numbers now? It was 3 before. What's it going to be when we add 1 to each value? You might be able to do that intuitively, but if you just crunch the numbers, 2 plus 3 plus 7, that's 2 plus 3 is 5, 5 plus 7 is 12, divide that by 3, you get 4. If you can't do it intuitively, then you can do it the good old-fashioned way with hard work. But you can maybe think, well, if I'm going to add 1 to each individual number in the distribution, that should bump up the entire mean by 1, which is exactly what it does. And you get a mean of 4, right? And what happens to the standard deviations? We'll look at this really quickly without crunching the numbers the same way again, but 4 minus 2 is 2. Square that, you get 4. 4 minus 3 is 1. Square that, you get 1. 7 minus 4 is 3. Square that, you get 9. So it's going to be 4 plus 1 plus 9 to get 14 for the standard deviation, or that's the sum of squares. You divide that by 2, so on and so forth. You get to the same spot for the standard deviation. So adding 1 in this case is going to bump up the mean by 1, but it's not going to change the standard deviation because these differences are all basically the same as they were before. You're not changing them in any sort of adding or subtracting way, right? Yeah, so that is our first little example of one thing we can do with the data which changes the mean but not the standard deviation. Let's take a look at what happens when we multiply every value of this little distribution by 2. So now the data is going to be 2, 4, and 12. We started out with 1, 2, and 6. Now we have 2, 4, and 12. And again, in class, I just say, what's the mean of these guys? You can use a calculator to figure it out. You can use a pencil and paper. You can use R as well. We saw how to do that too. I'm going to do it just talking you through it. 2 plus 4 plus 12, that's 6, plus 12, that's 18, divided by 3 is 6, right? So that's nice. We started out with a mean of 3. Now we doubled every value. We're going to get a doubled value of the mean too. It's going to go from 3 to 6. So that kind of makes sense. But what happens when we look at the standard deviation now? So we've got 6. And before we had these sort of squared sums of differences, squared deviations of 4, 1, and 9 that added up to 14. Now we have 6 minus 2, that's 4. Square that, you get 16. 6 minus 4, you square that, you get 4. 12 minus 6, you square that, you get 36. Now it's going to look a lot different. So 36 plus 16 plus 4 is 56. And we're still going to divide that by 2. There's n minus 1 equals 2 in this particular case. 56 divided by 2 is 28. And so our standard deviation is going to be the square root of that. It's going to be square root of 28. And if we go one step further, I didn't write this out explicitly, but you can look at this in a slightly different way. I boiled it down to 2 times the square root of 7, which is a nice way to put it because we have, I might do it this way. Actually, no, I'm not going to do that way. So we started out with standard deviation of square root of 7. With our original set of data, we multiplied every value by 2, and now we're getting a standard deviation of 2 times the square root of 7. So we're kind of getting the same effect on the standard deviation as we got on the mean before. I'm going to do this a little bit better. This is probably, there's a general rule of thumb with lecturing is you should always show rather than tell. So I should really shut up and stop talking and make this explicit in this lecture, but sorry, too late now. Lesson may be learned. We'll see how it goes in the future slides. But anyways, I'm going to make this explicit and say that if you have the square root of 28, you can kind of simplify that a bit by saying the square root of 28 is equal to the square root of 4 times 7. And that's how I can kind of factor out this 2 here. So the square root of 4 by itself is just 2. 2 times 2 equals 4, so the square root of 4 is 2. And that you can bring that 2 out and just say the whole thing is equal to 2 times the square root of 7. Again, this is doubling the standard deviation when we multiply every value by 2. We also doubled the mean value when we multiply every value by 2 as well. So adding will affect the mean but not the standard deviation. Multiplying will affect both of them. So now what do you think will happen if we multiply every value by 2 and then add 1 to each of those values? You can maybe make a guess. I will show you what happens on the next slide. I think I'm going to stop talking about the arithmetic because, yeah. But we start out with 1, 2, and 6. You multiply every value by 2 and then add 1. So 2 times 1 plus 1 is 3. 2 times 2 plus 1 is 5, so on and so forth. So we get 3, 5, and 13. And maybe you can see if you add those all up and divide them by 3, the mean is going to be 7. And hopefully this shouldn't be too much of a surprise intuitively, even if you haven't worked through all the grunt work to figure this out with your calculator or whatever. But the original mean is 3. Multiply that by 2, you get a mean of 6. Add 1 to all those values, you get a mean of 7, right? It's doing the same, having the same effects as the previous operations did separately. We're just doing them, combined for the same data set in this particular case. Yeah, and so maybe you can guess as well. You can work through the math if you want to, but if you do this for this particular data set and get 3, 5, and 13, and then figure out what the standard deviation is, it's going to wind up having the same effect as multiplying everything by 2, because the addition doesn't have an effect on standard deviation. So standard deviation here will be 2 times the square root of 7. Yeah, so I'll get to the summary slide here in a second about the effects of addition and multiplication on these little data sets, but these operations are all called linear transformations of the data because they follow the format of the equation for a line. So y, if you remember back to high school math or wherever you might have learned this, the equation for a line is generally expressed as y equals the slope times x plus the intercept. So y being a variable here, which depends on x, another variable. The relationship is that you multiply the x variable by the slope, or what's called the slope, and then you add the intercept to it. Kind of more crucially there, though, is that you have to think in terms of the operations. These are the two operations we've been playing around with, multiplication and addition. So that's what will happen if you try to linearly transform your data. It can have, well, like I said, and I'm going to put this on the next slide here. The multiplication can have an effect on both the mean and the standard deviation, and addition will have an effect on the mean itself. But both those operations are involved in calculating the equation for a line. And I'll give you a graphical example of that. I'm not going to talk you through it or write it on a whiteboard. I'm just going to grab a random graphic off the internet and then show it to you. So here's our equation for a line, y equals slope times x plus intercept. Normally, again, in class, I will ask people if they remember what the equation for a line is. And a lot of times people come up with this equation, which is the one I learned a long time ago when I took algebra for the first time as a youngster. But it's often expressed as y equals m times x plus b. And I don't know exactly why they use m as the representative of the slope in this equation. You'll see as we get into the next set of slides, another way to express this is y equals a times x plus b. That makes a little more sense because this is sort of ordered in terms of slope and intercept. But this is traditionally the way they describe it. And more crucially, though, well, first of all, I'm not going to use that notation if I can avoid it because it's a bit arbitrary. And if I don't understand it, I'm not going to be able to explain it to you. But more crucially, we want to know exactly what does this slope or what does this m variable represent. And the basic idea is that the slope of a line is going to indicate how much the value of y changes for every unit change in the value of x. So when I learned this in high school algebra class way back when, they talked about this representing the rise over the run. So normally when you plot out y and x in a two-dimensional graph, you have x on the horizontal axis and you have y on the vertical axis. So the run, if you're like a little kid learning algebra, is like how much are you running on this flat surface? You can kind of look at this in this particular case and say, well, if I have like a 1 unit change from 0 for x to 1 for x, I'm just making 1 unit change in x. But then the rise, how much does the line increase on this vertical dimension? That changes by 3 units. It goes from 1 to 4. So in this particular case, the y is going to increase 3 units for every 1 unit increase in x. That means the slope is 3. The rise is 3 over 1, which is the run. And you can see that in the equation where we have slope here times x is 3, or that's the m version here, it's 3. Yeah, hopefully that makes sense. The other part of this that we need to understand, and hopefully this rings a bell somewhere from your past, but the intercept of the line specifies what the value of y is when the value of x is 0. Give me a second. I'm losing all this water here in the sauna of my office. Anyways, yeah, so the intercept of the line specifies what the value of y is when the x is 0. And we can kind of already see this directly here because they've highlighted the point for us on this graph. But the x value when it's 0, y is going to be equal to 1. So we just kind of slot that variable in over here where it says b, or intercept, in this equation. We already know the slope is 3, so y equals 3x plus the intercept, which is 1. That's the equation for this line. And what we were doing before were just linear transformations of a particular data set. So if before we had sort of values like 1, 2, and 6, you can maybe think of those as like the x values. And then whatever we might have done on top of that, like 2x plus 1, for that final transformation we did, that would give you the y values that correspond to those x values. Yeah, the point is that the slope and the intercept of a line are all you need to know to describe that line mathematically. It's pretty straightforward. There's just like two crucial variables that get involved, and you know how to draw a line or understand the linear relationship between two variables. Okay, so like I said, these are examples of linear transformations, and I'm going to walk you through the summary again. So when we added or potentially subtracted numbers to a data set, that will tweak the intercept of the data set alone. So that's, again, our two operations were adding and multiplication. So adding or potentially subtracting here just is giving you like some intercept value for this linear equation. And we found out that what this does to the distribution itself is that it increases the mean of the distribution, but not its standard deviation or other measures of spread like the range, for instance. So the measures of spread are left alone by the addition procedure, but the multiplication will, or division for that fact, will increase or decrease the mean correspondingly, and it will also change the standard deviation by the corresponding amount. So if we double the value of x and getting y, then it's going to double the value of the mean, and it's also going to double the value of the standard deviation. And those are our two operations, multiplication and addition, basically, for a linear transformation. Okay, this leads me to how hot it is, and I think I'm really going to open up the door because it's a bit ridiculous, all the sweat that's pouring down my forehead, and this will make it slightly not as warm here. But in Calgary, houses are typically not made with air conditioning, and mine is not made with air conditioning, but it's pretty hot still, I think. I'm not going to tell you what the temperature is outside. I'm going to hold up this clock, my famous clock. It says it's 31.1 C. That's the temperature inside this room right now. Woo. I know in my head what that is in Fahrenheit because I'm an American who has been living in Canada for a really long time. And I can do the conversion in my head, but the crucial part of it is there's actually a linear relationship between how to express temperatures in Celsius and how to express temperatures in Fahrenheit. Often when I talk about, or generally when I talk about this in class, I ask people, well, do you know what this relationship is? And most people are like, no. So that's interesting too, being in Canada. So Canadians are sort of bilingual, as it were, between metric and what's called imperial units for temperature. So the old British system of measuring whatever. Canadians are usually pretty good at that because there is that connection historically with the British Empire. So Canada hung on to imperial units, I think, through the 60s, and then in sometime in like the 70s they might have changed, or maybe a bit earlier than that. So and then there's still, if you go to like the hardware store, they will still sell things in like that are measured in like inches or feet or something like that. And also I think even with pounds, Canadians are able to sort of make the transition between like pounds and kilograms, or like inches and centimeters, so on and so forth. But when it comes to the weather, Canadians are just Celsius. They have no clue what Fahrenheit is. And, that's not so bad, I guess. Although I personally prefer Fahrenheit. And it's just funny that sort of the most crucial example, Canadians can't do just kind of on the spur of the moment or have some intuitive sense of. But that's fine because that gives us a chance to learn something. So being an American who still uses Fahrenheit and prefers it to Celsius, I can tell you how to speak my language. By walking you through the math, basically. So most Canadians don't know this equation, but they do know sort of these benchmark points for what Celsius is supposed to represent. So this is supposed to be a rational system that came to us through the French Revolution, which historically, by the way, is why the British did not sort of adopt the metric system right away, because it was this French thing. And, why give up British tradition when you can be rational or irrational or something? I don't know. But the idea with the metric system is it was supposed to be rational, and it's supposed to be based on sort of these properties of nature. So why don't we make 0 the freezing point of water? Okay. And then 100 is supposed to be the boiling point of water. It gives you nice and easy to understand decimal landmarks for the state of water. And then the question is, what are the equivalent temperatures for Fahrenheit? And Canadians don't know that, and then when you tell them, they're like, "What the heck?" And I'm like, "Sorry." The benchmark points in Fahrenheit for these two numbers are 32 and 212 because Fahrenheit is not based on anything to do with water, really. So it seems a little bit funny. So we got 0 Celsius is 32 Fahrenheit and 100 Celsius is 212 Fahrenheit. And then these just seem like arbitrary numbers. There is... I once looked this up, and I can't remember the specific name of the article, but it's like a syndicated article that used to be published in sort of these like alt weeklies that you would see in like big cities that would tell you about like where's the best rock show that weekend, that sort of thing. And I can't remember. It's not News of the Weird. It's something else like Ask Chuck some question or something. And somebody asked Chuck like why, like what does 0 and 100 represent in Fahrenheit? And what he came up with was that 100 was supposed to represent the sort of average or normal human body temperature, which we now in Fahrenheit represent as 98.6, which by the way is 37 Celsius. Although so I'll say more about that in a second. So that's supposed to be human body temperature, but it's not accurate because it's 98.6 actually, but they guessed it was 100. And then 0, apparently the guy coming up with Fahrenheit was, I think he was Danish, or maybe he was selling it to the Danes or something. And then 0 was like colder than it ever gets in Denmark. So 0 is just like a really cold number, basically. And then 100 is human body temperature. So those were the landmarks for Fahrenheit. And maybe the French Revolution did better. And maybe that's why a lot of people use Celsius. But I will also say, interesting fact along the way, apparently human body temperature is decreasing on average. So I grew up thinking that 98.6 or 37 Celsius was the normal human body temperature, but most people apparently have a slightly lower human body temperature than that during the day. Who knows why? And apparently this has been decreasing over time or something. I don't know. So we're less warm-blooded. It doesn't matter for now. We're just talking about the numbers, and let's try to convert one scale to the other. But then we'll have this mystery in the back of our heads to think about as we're trying to fall asleep tonight. Okay, so I want to use those two benchmarks for freezing and boiling points of water to come up with a formula for converting Celsius temperatures into Fahrenheit. So Celsius is going to be our X variable, and Fahrenheit is going to be our Y. And we're going to, again, relate them linearly. It just turns out to be a little bit easier to go in this direction for a couple of reasons. Both the math works out nicely, and also people are familiar with Celsius and want to be able to convert it into Fahrenheit normally. Okay, so to calculate the intercept, we want to know what Y equals when X equals 0. And I kind of already told you that on the previous slide. So when X equals 0, when the temperature in Celsius is 0, that's the freezing point of water. And we know now that when water is at the freezing point in Fahrenheit, it's 32 degrees. So 32 is going to be our intercept in our linear equation. Okay, so that problem was easy to solve. The other half of this that we have to worry about is what's the slope of our equation. And for that, we need to know, like, for each change of 1 unit in Celsius, how much does the temperature change in Fahrenheit? So actually, I will pause here for a second. Maybe I should get a towel. I don't know. Yeah. Feel like I'm Alec Guinness in Bridge on the River Kwai. Remember that one? Anyways, so right. We have, how would you figure out what the slope is? So remember, that's supposed to be the rise over the run. How much does Fahrenheit change for each unit change in Celsius? Knowing what we know, what can we use to figure that out? What I want to do is to say, well, the difference between the boiling and freezing points of water in Celsius is 100 degrees. What is the corresponding change in Fahrenheit? So just, it's 100 degrees Celsius when water is boiling and 0 when it's freezing. That's easy to calculate. Thank you, French Revolution. In Fahrenheit, the difference between those turns out to be a relatively round number. 212 minus 32 is 180. So a change of 100 units in Celsius gives you a change of 180 units in Fahrenheit. So we kind of think of this as the rise. 180 is the rise and 100 is the run. So divide 180 by 100, that gives you the slope. So the slope in this case is going to be 1.8. And we already know that the intercept of the equation is 32. So there's our line. All we need to know to describe a line is what the slope and the intercept values are, and we're good to go. So our finished product is going to be this, where y represents the temperature in Fahrenheit and x represents the temperature in Celsius. Y equals 1.8 times x plus 32. And if you look this up in some guidebook for conversions or something, like it will often say y equals 9/5 times x plus 32, which is the exact same thing. 1.8 equals 9/5 and vice versa. Yeah, that's where that comes from. So I'm going to give you a few examples. So the basic one we started off with, like if the temperature in Celsius is 0, what does that give us in terms of this equation? Well, it takes this first part of this equation, the 1.8 times x part of it, and just reduces it to 0. And that leaves us with the intercept, 32. So that's the freezing point of water in Fahrenheit. What about the other side of that? So if the temperature in Celsius is 100, then we're multiplying 100 by 1.8. That multiplication, that product is 180. You add 32 to that and you get 212. Easy peasy, right? You're probably not ever going to have to do that conversion though. Sort of like a temperature you don't get in real life in the weather, and it's also a temperature you don't get like when you're cooking things either. Maybe it's a temperature you get in chemistry class or something like that. But a more realistic temperature in Celsius is 10. So in that particular case, it would be 1.8 times 10 plus 32. So 1.8 times 10, that product is 18. Hopefully that's easy enough to see. Add 32 to that and get 50. So that's, I think, kind of relatively easy benchmark to remember. Going between the two, like 10 in Celsius is 50 in Fahrenheit. Yeah, it doesn't really matter that you don't need to know this conversion for this class. You just need to know the principles of how we're going from one to the other. This is a linear equation, basically. And I will mention, this has actually gotten hotter since I started talking. I shouldn't have kept the door closed for many reasons. But it's 31.8 now. Wow. I can tell you off the top of my head that is about 89.24 in Fahrenheit, I think. Something like that. I got another value which is more relevant. The high temperature in Calgary today is 35 degrees, or was 35 degrees, which is really hot for Calgary. We'll talk about how hot that is for Calgary in the next lecture. But if we run that math through this equation, 1.8 times 35 is 63. Add 32 to it is 95. So just so you know, 95 degrees Fahrenheit, 35 degrees Celsius is warm. So as a public service, I will let you know that in Fahrenheit, 0 is really cold, 100 is really hot, and then 50 is neither hot nor cold. So that's why I kind of like it as a system, because we kind of have this range from 0 to 100. And in fact, if it's below 0 or if it's above 100, just like don't go outside. Just sit in your house where it's hopefully warm, like warmed by a furnace or like cooled down by an air conditioner, and then just like make your way through the day that way. And then 50 is like, yeah, I'd probably put on a jacket, right? Yeah, so it was 95 today in Calgary, so that's getting pretty close to really hot. And in fact, I think most Calgarians would say that's really hot. But it's fun. We may break the all-time record today. Again, not that it matters. So you may go ahead and forget everything you learned here. I use this kind of scale for my wife, who like always has to deal with me talking about Fahrenheit temperatures. And I'm like, this is so easy to remember. And she never does, but who cares? If you want to be a nerd, you can remember it. What I really want you to know for this class, though, is that Celsius and Fahrenheit temperatures are linearly related to one another. And it's a nice example of like a linear relationship from real life. Yeah, so I'm not going to say anything further about it today, although we'll talk about it a bit more in the future. I want to go back to that original data set that we were playing around with, and I want to play around with it a bit in R. So I'm going to have to move my windows around a little bit to do this. Just show you a few little tricks. So if I say, if I call this set of data test, and just say it's 1, 2, 6, those are my 3 data points there. I can sort of do these linear transformations to that set of data pretty simply in R. Just add 1 to the entire set of data. You get this new vector called test1, 2, 3, 7. We saw that before. And then, if I multiply it by 2, then I get, 2, 4, and 12, which is nice. And I want to say, what's the mean of that? Oh, it's 6. We calculated that before. Or what's the standard deviation. So we didn't look at the standard deviation in the original set, but it's 2.645, so on and so forth. The standard deviation when you double all the values is 5.29. 2.64 is the square root of 7. Actually, we can do it this way. If you square that standard deviation, you get 7. If you square the standard deviation of test 2, you get 28, which we saw before, so on and so forth. This is all checking out, right? And it's easy to do this using these sort of vector equations in R as well. So test 3 will give me those numbers, and then the mean is 7, like we saw before, right? So now I've got, I think we've seen this before. So ls, that tells me what is in the system here, what sort of information is encoded in R, this particular console. What I want to do briefly is show you that the fun part of this is that shape of the distribution doesn't change. Although this is a very boring distribution shape. If I just draw a histogram of it, it looks like this. This is my first set of test data, 1, 2, and 6. Yay, whatever. Let's draw the second set of numbers. Oh, it's same thing, same shape. You might notice the numbers down here changed. Yeah, so they just got slightly bigger, right? What happens when we do test 2? Oh, same distribution shape, but the numbers on the bottom changed again. Or test 3, so on and so forth. That doesn't change anything here. So these linear transformations are not going to change the shape of my data. But they'll just change sort of where I can find it on the x-axis, basically. And I'll have more to say about that in the upcoming lectures as well. But I want to have us learn a little bit more about normal distributions and the various properties first, and then we'll kind of come back to this issue. Ultimately, we're working up to a concept called z-scores, which is sort of like information you can get out of normal distribution based on a linear transformation of the data in that distribution. So I'm not going to say anything further about it now, but that's why we're kind of like talking about this to set the stage for what comes next, as usual. All right, I'm going to stop talking now, though, and cool down a little bit before I start the next lecture.